Okay, good day everyone. My name is Josipan Olivera. I am a student in the last semester of the master degree in physics from Simestap Zacatenco. I'm going to present my poster with the name Resonant Structures for light coupling based on phosphors. First, what is a resonant structure for light coupling? Well, this type of structures known as distributed Bragg reflector (DBR) or one-dimensional photonics crystals (1PC) are structures of alternate layers of crystalline or amorphous material that absorb very little or almost no electromagnetic radiation in the region of interest. In this case, it was chosen that the alternate layers would be silicon dioxide and titanium dioxide. This is because these materials have been extensively studied. There was already previous work carried out by the working group. One of the main characteristics of these structures must be the notable difference between refractive index of the materials. In the visible and infrared regions, the refractive index of silicon dioxide is approximately 1.45, and for titanium dioxide is 2.35. And this is good for constructive interference of light at fewer layers. The light fall on the mirror and it can be a shape that a certain region is reflected with reflectivity close to 100%. This can be used to improve the reduction of the emission of photoluminescent materials, mainly these that are being implemented in the conversion of energy probably used by solar cells into energy that can be used as is in phosphorus-based materials, for example. The deposition method proposed for this work is known as AACVD, or aerosol assist chemical vapor deposition. Here we have a sketch of the reactor and the process that it is followed. For the deposit of the alternate layers, the deposit method offers several advantages over methods such as MBE, ILD, or sputtering, since it does not require vacuum pressure, high temperatures, greater than 100 degrees, and the system can be modified to fit the needs of the deposit. Uh, well, what do we have? Suitable conditions were found for the growth of the materials. We found that the titanium dioxide began to deposit from 200 degrees. The deposition rate with temperature, flux, and distance from the substrate were varied to find a deposition rate of approximately 10 nanometers per 30 seconds, and similarly for the silicon dioxide. In the micrograph, we can observe that the ground for alternate layers with nanometric thickness is a shape by profilometry that the surface does not vary considerably in thickness on the measurable line. The XRD pattern showed that there is formation of the anatase crystalline phase for titanium dioxide and silicon dioxide isomorphism. At annealing temperatures greater than 600 degrees, the formation of the rutile phase for titanium dioxide can be observed. The formation is not complete, so we have both phases, but at temperatures around 800 degrees. This makes it more difficult to adjust the thickness with respect to the reflective index, since the rutile phase has a higher reflective index. Also, at temperatures of 500 degrees, we can see that the structure is polycrystalline in anatase, tetragonal and amorphous phase, but at 600 degrees, the predominant phase is anatase. The FTIR performed on the samples shows that it is necessary to carry out an annealing after the deposit of the titanium layer, since there is some contamination by functional groups in the film that damage the subsequent layers. Well, we use spectral ellipsometry to obtain the values of the refractive index and the layer thickness at different annealing temperatures, finding that the theoretical model predicts the behavior or reflectance for thin layers in the visible range, but fails. This is the visible range, but fails for thickness layers in the higher range, uh, due to the increase of the porosity of the layers. However, a reflectance greater than 95% is a type in the area of greatest interest. The adjustment was made by ellipsometry. The adjustment was made by ellipsometry to samples smaller than 100 nanometers for both materials and with a double layer with the values for the visible range, which is why the result is a fit better in the region that in the ear. Here we can see some samples. The color is characteristic of the region to be reflected. Conclusions. The expected reflectance fits the model obtained by ellipsometry for the layers and on 600 and 800 degrees. The thickness obtained by ellipsometry and estimated by SEM are as expected. The layer at lower temperature presents roundness or amorphous material that affect the refractive index. That AACVD is a technique that gives grounds of this type of structures in atmospheric conditions under ground temperature that can be used for future works in the doping of the layer or of the use for the other nanometric structures. The acknowledgement. Well, this is all about my job. If you have a question, you can send a message directly or by my mail. Thanks for seeing my presentation.